Introduction to probability. Let's talk about some vocabulary words to start with. So any event whose result is uncertain is called an experiment. And then the possible results of the experiment are called outcomes. The set of all possible outcomes of the experiment is the sample space, and any subcollection of a sample space is an event. So here we can see that one experiment or situation could be rolling a number cube, often called a die. And then the sample space, you'll notice, is written in the curly brackets, 1, 2, 3, 4, 5, or 6. Another event or situation could be spinning a spinner. And in this one, you could get red, blue, yellow, or green. So that would be your sample space. So an event on the spinner could be landing in blue. So I'd like you to find the sample space for each experiment. Pause the video and try this. So for 2 coins, you can get heads and heads, or heads and tails, or tails and heads, or tails, and then we put those in curly brackets. So a lot of times students will confuse this because they think that heads and tails and heads is the same thing. It'd be better if you think about this as having 2 different coins, like a dime and a quarter, and then it makes more sense. Like getting heads and a quarter and tails on the dime is not the same as getting tails on the quarter and heads on the dime. Try it now for 3 coins. So for 3 coins, you should have gotten these values, these outcomes in your sample space. And you'll notice that you have 4 outcomes when you have 2 coins are tossed, and you have 8 outcomes when the 3 coins is tossed. Now, 4 outcomes, that's the same thing as 2 squared, and then the 3 coins is the same thing as 2 cubed. So 3 coins, and then each coin, they only have 2 options, heads or tails. Now, I should point out that it's not always going to be that easy. It's not always going to be just doing a number to some power, but in this case, with the coins being tossed, it is that easy. The probability of an event. So if an event E has n of E equally likely outcomes, so this would be representing their number of outcomes for the event, this n with the parentheses, and its sample space S has n of S equally likely outcomes, so this is your total number in your sample space, then the probability of the event E is given by P of E, so the P is for the probability, and then the E is the event, so this is our proper notation for representing probability of an event, and it would be your number of successes divided by your total number of outcomes. Most of the time, I would just write it out, and I wouldn't really use this notation with the N, but that's what they mean, the number of ways that your event can happen divided by your total number of ways, or the number of things in your sample space, number of outcomes in your sample space. The probability of an event must be between 0 and 1 inclusive. So written as an inequality, 0 is less than or equal to probability of E, which is less than or equal to 1. So you can see over here in this diagram that if your probability is 1/2, then the occurrence of the event is just as likely as it is unlikely. And if the probability is equal to 0, then that event cannot occur, and we call that an impossible event. So an example of that could be, well, today is Wednesday as I'm recording this video, the probability that tomorrow is Friday. That's impossible because that's not how time works. And then if a probability of an event is equal to 1, then the event must occur, and we call that a certain event. Now there is a distinction between experimental probability and theoretical probability. Experimental probability is based on an experiment, and theoretical probability is based on reasoning, which is what will happen in the long run. Sometimes you can do both experimental and theoretical probability, and sometimes you can't do both. So one example where you can do both would be if you're trying to flip a coin and you're going to do it 100 times, and you keep flipping a coin 100 times, and maybe you find out that you get 60 times you get tails. And so then you might think, well, it's 60 out of 100 is my probability of getting tails on the coin. But you know that with a theoretical probability, there's an equal chance of getting heads as getting tails. And so then the theoretical probability would be 1/2. An example where you can do only experimental probability might be weather forecasting, because you can't actually know what is going to happen. You have too many unknown factors. Predicting student behavior, or really predicting any kind of behavior of a human being. If you're doing like running a club and you're trying to make a probability of how many people will join your club, well, you can't make that prediction based on theoretical probability. And then sometimes even with medical treatments, you don't really know what's going to do, so you just have to experiment with it and see what happens. So your experimental probability would be your number of successes over your number of trials, and your theoretical probability would be your number of successes over the total number of outcomes. All right, we're going to calculate this. Go ahead and pause the video, read through this, and try this on your own. You had to add up your total number of M&Ms, and there were 54 M&Ms. So 8 out of 54 is 0.1481. And then you have 10 orange, and so you get that number, and so on and so forth. So based on the experimental probability, you think that the theoretical probability of each color is equally likely, or 1 out of 6. And this is a little bit confusing the way that it's written. In other words, do you think it's actually 1 out of 6 chance that you're going to get a color, like an individual color from a packet of M&Ms? And it seems to me that it is not going, based on my theory, or sorry, based on my experiment, it seems that you have a higher probability of getting brown. So you can say something along the lines of, no, based on the experimental probability, there's not an equal likely chance of getting each color, because you can see that it seems you have a higher probability of getting brown in your packet of M&M. Mutually exclusive and inclusive events. Mutually exclusive events are events that cannot happen at the same time. So we can see in this Venn diagram, this would be the probability of A and the probability of B. These circles do not overlap. An example of mutually exclusive events would be the probability of a student being a sophomore and a senior. You can be one or the other. So when we write this with our notation, we're saying the probability of A or B, and that's the probability of A plus the probability of B. So if you wanted to say, what's the probability that the student is a senior or a sophomore? Well, you would have the probability that they are a sophomore and then the probability they are a senior, and you just add them individually. You don't have to worry about any kind of overlap. Overlap occurs over here with inclusive events. This is when events can happen at the same time. So you can see in the Venn diagram that the two circles overlap. So you have the circle A and the circle B, and then in this section over here where they overlap, that would be the union. So that symbol right there is for union. You may have seen that in Algebra 2 when you talked about domain and range. So an example could be the probability that a student is a senior or on the volleyball team. So you could be a senior or you could be on the volleyball team, but you could be a senior on the volleyball team, but you don't have to be both, right? Like, so you can be a sophomore on the volleyball team. So the notation here is going to be the probability of A or B. So same thing, like I said, senior or on the volleyball team. It's the probability of A plus the probability of B. And then you want to subtract the overlap, the probability of A and B. So you'd want to subtract the students that are both seniors and volleyball players, because you've already counted them when you counted the number of seniors, or the probability of being a senior, and the probability of being on the volleyball team. So you don't want to count them both twice. Okay, pause the video and try this example. All right, so it does help to be familiar with playing cards for these types of questions, but I will provide a diagram for those of you that are not familiar with playing cards. So the probability of getting a heart, well, there are 13 hearts in a deck, so that's going to be 13 out of 52. And then the probability of a face card, and students always ask what's a face card, and those would be just the jack, queen, and the king, and each suit, and there's 4 suits, so there's 12 out of 52 face cards. So face card is jack, queen, or king. A lot of students want to argue that an ace is a face card, but there's no face on the ace, so an ace is not a face card. So then the probability of being a heart and a face card would be your jack of hearts, your queen of hearts, your king of hearts, and there's going to be 3 out of 52. So overall, we say the probability of getting a heart or a face card would be 13 out of 52 plus 12 out of 52, and then we're going to subtract 3 out of 52 because, again, we have already counted all the jack, queen, king of hearts when we counted all the hearts, and then we counted the jack, queen, king of hearts when we counted face cards. So that's why we have to subtract, because we don't want to count them twice. So that's going to be 11 out of 26. Now you can give your answer as 11 out of 26, or if you want to round, that's going to be 0.4231. Either answer is acceptable. You actually could even give 22 out of 52. Independent and dependent events. The occurrence of one event does not affect the occurrence of the other. And then an example of that would be selecting an ace and then a 7 from a deck of cards if you replace the first card. So it doesn't matter if you get an ace in the first draw and you put it back, you still have an equal chance of getting a 7 on your second draw. Now, if you kept that ace in that first draw, then your probability of getting a 7 would be 4 out of 51 instead of 4 out of 52. So the replacing part is very important here. So over here, the dependent events will be the events that are affected by the outcome of what happened before. So like I just said, the probability of selecting an ace and then a 7 from a deck of cards if you do not replace the first card, because it would reduce your number of your outcomes down to 51 instead of 52. So for both of these situations, this is going to be like and probability of A and B, and that's going to mean multiply. So whenever you see the word and, you can think about it as multiplication. So the probability of selecting an ace and then a 7, So it would be an ace first and then a 7. Depending on if you replace or don't replace, it could be dependent or independent. Okay, pause the video and try number 4. So for this one, Anna chooses a box and then replaces it, so that makes it independent. Sebastian does the same thing. The probability that both choose a brown box. So let's write down our proper notation here. The probability that Anna and Sebastian choose brown will be, well, there's 9 brown boxes and there's 15 total boxes. So that's for Anna, and she puts it back. And so then Sebastian gets the same thing, 9 times 15. So that's 81 over 225, which is also about, well, not about, but it's exactly 3.6. Should make that an equal sign, not an approximately equal sign. Okay, then for part B, Anna chooses a box and then keeps it. And then Sebastian chooses a box, and probably they both choose brown. So we want to write the same notation. So Anna, again, is going to have 9 out of 15, but then she's going to keep that box, and we're going to assume that she has a brown box. And so then that's the probability of both of them choosing brown, right? Is that she has the brown. And so then 72 out of 210, or approximately 0.3429. So you can see the probability went down a little bit when she keeps that brown box. Complement. The sum of all probabilities in the sample space is equal to 1. So that's a very important statement here. So you can think about this with like your die, your number cube, as it were, right? You've got for getting a 1, you've got 1 out of 6. For getting a 2, it's 1 out of 6. 6 is 1 out of 6. And so if you add all of those up, you're going to get, of course, 6 out of 6, which is equal to 1. So that's a pretty simple example of why when you add up all the probabilities of in the sample space, you're going to get 1 every single time. So the complement of an event, notice the spelling here is with the E, of an event E is a set of all outcomes in the sample space that are not in E. So if E is an event, then E with the apostrophe, we can say E prime, or not E, however you want to read that, is the complementary event. So here we can see that you got the probability of E plus the probability of not E is equal to 1. You can also write that as probability of E plus the probability of E with the apostrophe, which again, you can read that as E prime or not E is equal to 1. In a Venn diagram, you're looking at the circle of the event inside of what we call like that would be your sample space. So the event is happening as E, the event not happening is everything that's outside of the circle. Let's have a look at number 5. So we've got a quiz. There are 6 true-false questions, and at least 4 correct answers are required for a passing grade. So they're guessing at each answer, right? True, false. What's the probability of getting a passing grade or getting a failing grade? So for part A, getting a passing grade, you need at least 4. So we're going to say 4 or 5 or 6 correct answers. So here's the thing. The denominator is going to be 6 true false questions. So that's just going to be, there's 2 choices, true or false, and you have it 6 times. Now the number of ways that you can get 4 of those correct, we can do a combination. So a combination of 6 C4, 6 questions, and you want 4 of them to be correct. And then for 5 correct, so we're going to put an and here because the or means to add. I'm sorry, yeah, the or means add. 6C5 divided by 2 to the 6th power, and then 6C6 divided by 2 to the 6th power. Now, for the 6C4, you have to think like, well, I want to get 4 of them correct out of the 6. So maybe it's like correct, correct, and then wrong, 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 or sorry, just 2 wrongs. And or maybe you get correct, wrong, correct, 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 wrong. Or maybe you get correct, correct, wrong, correct, and so on. So rather than trying to figure out how that's going to happen, we just think of, well, anytime that the order doesn't matter that you have of your choices, right? You've got 6 questions and we want 4 of them to be right. So that's why it's just going to be 6C4. So which 4 questions are you getting right? Are you getting numbers 1 through 4 right? Or are you getting number 1 and then number 3 and then number 4 and number 5 right? And so on. Hopefully that makes sense. So when you add all that up, you're going to get 22 out of 64. And by the way, just to go again about that combination, how many ways would there be to get all 6 questions correct? Well, there would only be 1. And you can check in your calculator that 6C6, 6 combination 6, is equal to 1. So anyway, we're at 22 over 64, which is equal to 0.34375. For part B, the probability that they are failing, well, if the probability they are failing, you could do the probability of 0 or 1 or 2 or 3 correct. You have four different ones, 1 or 2, 3, or 0, 1, 2, or 3. Or you can actually do the complement. That's going to be 1 minus the probability of passing. So that's going to be 1 minus 22 out of 64, which is 42 out of 64, which is equal to 0.65. I went to more decimal places because it was exactly this number. And I also want to point out the whole at least business. Okay, at least 4 correct means the 4 or the 5 or the 6. So that's important. And then the idea here also is that you can use a complement for something like this if it's a pass or a fail. So failing would be getting 0, 1, 2, or 3. So you could do that part of it the same way that we do 4 separate fractions there, like we did in part A, or it's a little quicker just to do the complement. All right, pause the video, try number 6. So for this one, we want to write the probability that we're getting all 3 of the people that are going to be women. So we can do a combination again. So of the 3 women that are that are sales representatives, we're going to choose all 3 of them. You'll probably figure out there's really only one way for that to happen. Divided by the number, your sample space there, which would be the 9 people that are sales representatives, C3. So that's going to work out to be, this actually works out also to say 3 out of 9 times 2 out of 8 times 1 out of 7. Works out the same way, and that gives you about 0.0119. So that's like 1.19%, right? 1.19%. So you don't have to write the percent, but just bringing up here, so based on your answer, is there reason to doubt the manager's claim that the 3 people were selected at random? Yeah, I would say that there's some doubt here. If there's only a 1.19% chance that the 3 people selected would all be the women, there's definitely some doubt there. So you can see what I have here. Yes, there's evidence to doubt the representatives were chosen randomly because the probability of all 3 women being chosen is only 1.19%. So this doesn't prove that the inclusion of all 3 women was intentional, but it provides evidence that it may have been. The end.